We're going to write an equation for the rational function with the following features. And there are 5 bullet points here. Go ahead and take a moment, read them over, and then we'll get to figuring out what the function is. Let's start with a sketch of the graph. I know that's not technically part of the requirement. I find it easier to figure out how to write the function from the graph. So I'm going to build a graph as I go along. One sec, marker. Here we go. I'm going to start with XY axes and look at end behavior and just go down that list. I'm going to start with the end behavior. As x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x approaches positive infinity. Both ends, therefore, point up on this graph. So out way far at the extreme reaches of the graph, I need this graph pointing up. Not only do we show the end behavior on the graph, but let's also make a note of what that means about the rational function, whether it's top heavy, bottom heavy, or equally heavy. When you have end behavior that approaches infinity in either direction, that's going to suggest that you have a top heavy function. Not sure exactly how to use that just yet, but I'm going to save it there for later. The next detail, the x-intercepts are at -4 and +3. I'm going to approximately place them on the graph. Let's make a note about what that means for the function itself. The x-intercepts happen when the y value is 0. And so that means the output of the function is 0. And I've got a rational function, some polynomial in the numerator, some polynomial in the denominator. And to have that whole function equal to 0, that means I'm going to need the numerator equal to 0. So the y value is 0, meaning the numerator of my function is 0. Because I know what the two zeros are, I can write them in factored form. Let's start writing down the function. Factored form, -4 and +3. Now, whatever else is going on with this function, such as its denominator and such as its leading coefficient, I don't know yet what those are. But I do know that I've got those two factors in the numerator to create these two zeros. Let's go on to the next detail. You'll notice this is kind of feeling a little bit like doing a puzzle. I don't know about you, it reminds me a little bit of Sudoku. The next detail tells me that as x approaches 2 from the left, f of x approaches negative infinity. And as x approaches 2 from the positive direction, f of x approaches positive infinity. So I wrote down that this is describing one vertical asymptote at x equals 2. We're going to approach, what did I just say? Positive infinity? No, negative infinity and then positive infinity. So here, negative infinity. Here, positive infinity. Now, just to kind of put a ribbon on the thing that we've done so far with all these little arrows on the graph and those points I've plotted, The end behavior and the local behavior around vertical asymptotes allows me to look at what's happening to each end of the branch. The local behavior in between those arrows, we still have yet to figure out. Let's make a note here. Vertical asymptotes. What does that mean? X equals 2 is not in the domain in this function. So this is going to tell us domain restriction. Meaning X equals 2, not possible in this function. That's going to tell me spots where the denominator would be equal to 0. Let's add to the function that we're building over here. At X equals 2, this function is undefined, meaning at X minus 2 in the denominator, the function is undefined. Moving on to the next detail. I have a y-intercept at 0, -6. Plot that on the graph. Let's think about what the y-intercept means. The y-intercept occurs when x equals 0. This is going to indicate something to us about the stretching feature of the function. Or the leading coefficient. There's going to be an a value in that space that we have to figure out. I just noticed a detail that I want to go back and catch and fix that I didn't mention before. I notice here that I can play a pretty nice game of connect the dots here to here to here. Here to here to here, it looks like I need to bounce at 3. So I forgot to mention multiplicity. Multiplicity is related to the x-intercepts. If both ends of one branch of a rational function are headed in the same direction, we're going to bounce at that 0. And that's going to indicate a multiplicity of 2 here. Totally forgot that. And that would be important here. Now we can deal with this y-intercept thing. To solve for the y-intercept value, to solve for the a value, you're going to need to use the fact that when x is 0, y is -6. So I'm going to substitute that in here and solve. This is a nice, neat evolution of the function. So let me go ahead and do that over here. Now, according to my algebra here, the a value is 1/3. So can rewrite the function, and I think it's done. The 1/3, to keep this written in the most neat and compact form, I want you to split the 1 and the 3. Please don't try to do that kind of nonsense, right? Because now I've got a complex fraction and it's just not mathematically appreciated. So there is my rational function that has all of the features described originally. I'm going to go ahead and finish off the graph because, heck, that's like a 2-for-1 problem at this point. And there you have it. How to write the rational function from descriptive text using everything in red here. Let me put a box around that. This will be helpful. Best of luck practicing with your own problems and/or the homework.